This lesson is part one of rational functions. A rational function is a function of the form f of x equals p of x over q of x, where p of x and q of x, the numerator and the denominator, are both polynomials, and where the denominator q of x does not equal 0. The domain of a rational function f consists of all real number inputs for which q of x does not equal 0. So in part one, in this lesson, we're just going to tackle finding domain restrictions in order to graph a rational function. As I mentioned before, a rational function will be undefined for values of the variable that make its denominator equal to 0. Notice that we have a linear expression in the denominator. So if I take that 2x minus 3 and set it equal to 0, I can solve for x and find any values of x which will make the denominator 0. So I get 2x equals 3, x equals 3/2. Just to check that, let's take the original expression and in place of x put the 3/2. The 2's cancel, and I get 3 minus 3 equals 0. Thus, x equals 3/2, the function is undefined there, and the domain of the function will be x such that x does not equal 3/2, or in interval notation, x is an element of negative infinity to 3/2 non-inclusive, united with 3/2 non-inclusive to infinity. Let's see what the graph of that looks like. So I'm going to go to menu and trace and graph trace, and I'm going to key in the point, the value for x 3/2, and I'm going to hit enter, and we see the result of what happens here. We've got a vertical asymptote with the equation x equals 3/2. And I notice down here 1.5 or 3/2, the function is undefined. So that results in a vertical asymptote with equation x equals 3/2. Our next example, example 2, notice that we have a quadratic in the denominator. So to find any values of x that will make the denominator equal to 0, I either need to factor it or use the quadratic formula. This looks like it will factor fairly easily into x minus 4 times the quantity x plus 2. And so x minus 4 equals 0, or x plus 2 equals 0, and I get x equals 4, or x equals negative 2. Let's see what the graph of that looks like. So I know that I have a domain restriction at negative 2. Let's key that in. So I need to go to menu and trace and graph trace and key in negative 2. And I see once again that x equals negative 2 is a vertical asymptote, and down here it tells me the function is undefined at negative 2. Let's key in our other domain restriction, 4, and I notice that that results over here in a vertical asymptote at x equals 4, and it also tells me down here that the function is undefined when x equals 4. So our domain then, let me move this up a little bit, becomes this. To help you think about that, let's put the values of x where the function was undefined. So it was undefined at negative 2, so I'm going to block that off, and positive 4. So basically, I can have any value of x going down to negative infinity, so that's this part here. So x can be any real number from negative infinity to 2. Then I have to stop at 2 and not include it. And then I can pick it up, any real number between negative 2 non-inclusive and 4. And then this last part, any real number from 4 to positive infinity. In our next example, I notice that I don't have a constant in the numerator anymore. I have x minus 4. I'm just going to group that together. I'm going to factor the denominator, the same expression as before, x minus 4 times the quantity x plus 2. But the difference here, you'll note, is that there's a common factor in the numerator and denominator, resulting in the expression 1 over x plus 2. Now, let's see what that ends up looking like. So let's go to the graph of that function. and I'm going to go to trace and graph trace, and I'm going to look at -2, and I see that yes indeed, I do have a vertical asymptote with the equation x equals -2. And let's plug in that other domain restriction 4. So here I see it, I see a line at 4. It looks as if the graph is continuous at 4, but this is telling me it's undefined. What's actually happening here is there's a hole in the graph. So let me go back. So what we have so far is we have a vertical asymptote with equation x equals -2, and we have a hole in the graph with coordinates 4, which was my removable discontinuity. And to find out the y value, I'm going to plug 4 into the simplified expression, and I get 1 over 4 plus 2 equals 1/6. So I have a hole in the graph at 1/6. And the domain of this function is the same as the previous one, even though the 4's, the x minus 4 factors cancel out. 4 is still a domain restriction for this problem. My next example here, the x squared plus 1 is not going to factor for me, but if I set that equal to 0, I see that I get x squared equals -1, x equals plus or minus the square root of -1, or x equals plus or minus I. So what this is telling me is that there are no real number inputs for x that will make my denominator x squared plus 1 equal to 0. And that makes sense if you think about it logically. If I square a number, the smallest it can be is 0. And if I add 1 to that 0, I'm going to get 1 in the denominator. Otherwise, it's a positive number, and when I add 1 to that, I'm never going to get 0. So this function has no domain restrictions, and the domain is x is an element of -infinity to +infinity. Recap. Define any domain restrictions of a rational function. Factor both the numerator and the denominator. And we do that in case there are any factors in common that will be removable. If the numerator and denominator do not have any factors in common, then there is a vertical asymptote in any values of the variable that make the denominator equal to 0. So in this case here, my numerator factors into x plus 1 times the quantity x minus 1. It's a difference of 2 perfect squares. My denominator, x plus 2 times the quantity x minus 2, another difference of 2 perfect squares. There are no common factors, so my denominator will equal 0 when x equals -2. It will also equal 0 when x equals +2. So these are the equations of my vertical asymptotes. If I go back to the graph, and I look at that, let me remove these from the last one. And, no, that's not the right graph. And I think I may have forgotten to put that graph here. Oh, I'm sorry, this was the graph of the previous one where the domain was all real numbers because the x squared plus 1 in the denominator, and so I see that it doesn't have any points of discontinuity. And here's the one we just did. So if I go menu trace and graph trace and put in -2, I see that I get a vertical asymptote at x equals -2. If I put in +2, I see I also get a vertical asymptote there. Okay, so our next point was if the numerator and denominator have a factor in common, there's a hole in the graph at the value of the variable that makes the common factor equal to 0. So here the numerator, x plus 2, quantity x minus 2. The denominator, we end up with x plus 4 times the quantity x minus 2. And we see that we have a common factor of x minus 2. So we will have a vertical asymptote, and that will have equation x equals -4. And we'll have a hole in the graph with coordinates 2, comma. And what I need to do is plug 2 into the expression, simplified expression, x plus 2 over x plus 4. So I get 2 plus 2 over 2 plus 4 equals 4/6 or 2/3. So that's the location of the hole in the graph. And my domain, my last one, If there is no value of the variable that will make the denominator equal to 0, then the graph does not have any points of discontinuity. And like our previous one, x squared can only take on values of 0 or positive, and when I add that to 5, I'm never going to get 0 in the denominator. This ends part 1. Stay tuned for part 2, where we'll talk about the x and y intercepts of a rational function.